Well, let's consider a free body diagram for a slightly more complicated situation. We're going to do the inclined plane. So the standard drawing looks something like this. An angle here, okay, and the object sits on the inclined plane like so. Now, what makes this complicated is that some of the arrows don't point exactly the way you might expect them to. So, for example, the weight of the object points straight down towards the center of the Earth. Okay, if there's friction, it's going to point in this direction, opposite motion. Let me just make that a different color. If there's friction, it's going to point up this way. Okay, now what's really confusing is the direction of the normal force. The normal force is normal to the surface, so the normal force pushes up this way. And then finally, if we're just trying to figure out which way the object is likely to move, if it's going to do anything, it's going to slide down in this direction, right? That's the direction of motion. All right, well, what can we do here to make this problem a little bit more simple? Well, the first thing, of course, is to make the free body diagram. So the arrows up here are complicated. Let's make it a little bit simpler. So our object becomes a point. The weight now pointing downward, straight this way. We have the friction, if there is any, pointing up this way. And we have the normal force pointing this way. All right. It is usually convenient to create a coordinate system which is aligned with as many arrows as possible. So you can see that the frictional force and the normal force are perpendicular to one another, and so it actually is convenient to tilt our coordinate system in this direction. Okay, so we can let this be now the x direction and this be the y direction. Let me just label these so that you can keep track of what's going on. So we have the normal force here. This is the normal force. We have the frictional force over here. Here's the force of friction. And we have the weight here. Okay. And now we've tilted this coordinate system a little bit. So let's just take a quick look at what is going to be the direction of alpha. So if I tilt this system, then I'm going to get an angle. So if the system is let me change that one. I think the angle alpha is going to be this number here. Okay. There's a lot of ways that you can reason this out. One way is to say, okay, well, if I tilt the coordinate system by an angle, then this arrow is going to sort of rotate well, not the arrow, but the axes are going to rotate in the same direction. So when alpha is 0, W will be pointing straight along the y-axis. But when alpha increases, you can see that it increases with respect to the y-axis. You can also do some, parallelogram type drawings to make sure that you've got the angles correct. So this is the free body diagram. Getting into the math of things is now a little bit complicated. So the next step on all of these is to separate the x and the y components, okay, according to this diagram here. So the x components okay, this is going to have f sub f in the plus x direction minus w x, okay, the x component of the weight, okay, and that's going to be equal to m times a in the x direction. Notice that there's the minus sign here. The minus sign is because this is the direction of w sub x. right? That's the x component of w. It's pointing in the negative x direction. All right. Now, the y components are going to be given by the normal force in the y direction minus w in the y direction, right? Get the y component of w, and that's going to be equal to m a sub y. But because the object cannot accelerate in the y direction, right? It can't like go into the plane. It can only slide along the plane. A sub y is going to be equal